Okay, so let's keep going. We're going to draw now the tertiary beam members that go, again, in that direction and are offset a certain distance from our primary, off the center line of the primary. So to do that, we're going to need a construction surface, because we're going to need to take sections like we did last time, like we did in the Rhino file. So we got to go back a little bit. So let's go, we left off kind of over here. Let's scroll back just a few clicks. And remember these offsets, the offsets that we use to divide, to find basically the starting point for our secondary structure. So these offsets we'll start with, okay? And we're gonna loft them together to form that construction surface. So let's go to Surface, Freeform, Loft. And remember, you have to right-click on this and flatten it. And that's going to make our surface for us. And this is what we're going to use to draw our sections through it to locate those tertiary members. The other thing I'm going to do is I'm going to bring this down and kind of start a new area of the script here. Because we've got an area over here that finishes out our primary beams. Oops. Never mind that, but there's our primaries. We have an area that, like a chunk of the script basically here, that draws out our secondaries. And now I'm going to start another chunk down here that draws the tertiaries, and that just helps keep me organized so that I can put a box around this and always find really quickly where I need to make edits later on if I open this up a couple days later or something like that. Okay, so the next step is to offset this, because we know that this surface is actually drawn through the center of all of our secondary beams, and that's not what we want. We need the tertiary to rest on top of these, right? So we need to do an offset. So let's go over to Surface and Utility, and you'll find the offset surface component here. You can go ahead and plug that in. The distance we need to set as, again, a factor of the units that we're working in, which is in feet, and we want to actually offset that to an inch dimension, like we did before. So we just need to do a little division again. So I'm going to do that again. I'm going to go to Math, Divide, grab a panel, type in 12, plug that into B, and we can now set a custom parameter into A, which I'm just going to set to something like 5 for now, which is probably not enough, but we'll set it to 5 for now, and then plug that into D like that. And I'm going to turn off my original loft, because you can see that overlapping preview starts to get confusing. So now the offset puts the surface above, just above the secondary blue beams as we have here. And this is basically because we now have it 5 inches above that center point, which these are drawn at 6 by 6, so that's 3, and that gives me an offset basically of 2 inches. But if I wanted to not have to do the math on this, and if I wanted to just set that exact offset using a dimension without having to kind of overcompensate, if you will, we can do that as well. And to do this, I'm just going to introduce how to just write a very simple equation. And the equation is basically x times 2 plus y. And the x value is actually the value that we used here, right? This is the value that we used to set the size of that secondary beam. And we need that value, because if we change this value, it can trigger a reaction where it changes also the offset automatically, so we don't have to change 2 parameters in order to get the same effect. Because if we make this thing bigger, and I'll show you how that works now. If I make that bigger, the blue beams will get larger, but now I have an intersection and collision between all of this stuff. So we got to update all this so that we don't have that problem. So we're going to leave that at 3. And then I'm going to go to Math, and you'll find the little FX evaluate component over here under Script. Looks like this. And we have an X and Y input. You can add or subtract them. We're only going to need 2. And go ahead and double click on the evaluate component right in the center and type in our equation. So that's x times 2 plus y. And the y value is the one that we're going to use as our offset. And the x is the value that we use to set the size of the beam. So this is going to go red until we give it everything it wants. So let's put another panel in here and drop in a 2. And this is the exact dimensional offset. So we should see no change here. Well, maybe we'll see a little bit of a change. So we can go ahead and replace that value. So we don't necessarily need that anymore. So now every time I make an update to this, the surface will also increase, and you can see that happening there. We have other issues with this that we can fix a little bit later, which is a potential collision here. So we may need to update that offset in just a second, and I'm going to make that offset a little bit smaller just for now. You'll see that there's a couple different ways to do this, and some of you are already probably figuring that out. And that's fine. You can go ahead and plug in whatever equation you think makes more sense. You can even just add this value to another value and also get the same effect. The reason why I did it this way is because when we actually draw the thickness of those tertiary beams, that ends up making a difference because the offset will have to get larger. So what I've done is I've basically compensated for that already just by multiplying this by 2 because the tertiary beams will be the same size. So it's just a little bit of thinking there. But again, you can customize that. Let's go back to this gap here, and I'm going to increase that because I noticed that there's a little bit of a collision. Okay. We're good now. Okay, let's keep working. Okay, and this next step gets a little bit tricky, so I'll try to take it slow. What we want to do is find an endpoint to all of these curves. And we want to offset those points a distance away from the center of our primary beam. That's going to be the location for a section through the surface, and that section will become the rail that we'll use to sweep across to actually draw our tertiary member. You might recall we did this last time when we drew a sphere and we intersected this profile, and that intersection found the location for our sections. We're going to do it slightly differently because manually it's a little bit, I guess manually you could do it a little bit differently. All right, the first thing is we need to locate the point, basically the start or end point there for those curves. So what I'm going to do also is, again, I'm going back to this offset here. I'm going to place a little relay right there because this will help keep my script clean, and it'll help me make new inputs from that data set down here without having to go all the way back up to do that. So I'm going to go to curve, endpoints from analysis, and you can see that there's now points drawn right there. And I believe, if I turn that off, I believe the start point is the one we're looking at closest to our screen. Actually it is, so that's good. And we only need one of them, we don't need the other one. The next thing I want to do is I want to move that point in the x-axis a distance that's going to determine basically my tertiary beam offset. Okay, so let's do this. Let's double click in here, type in move. It's a little bit faster. The points that I'm moving are these points. The axis that I want to move against, or the translation vector, is going to be in the x-axis. So I want to just double click in here, type in x, find the unit x component. And now I have to give this a magnitude. I've got to give this a distance. I got to put strength on that vector so that it actually moves something. I'm going to go ahead and just plug that in for now. And you can see that I've moved it a unit 1 over to the right a little bit. But I want to move it both directions. So I'm going to double click, type in reverse. The first component down here, at least on my screen, is the reversed vector. You can also find that by going to vector, vector panel, and reverse. And then I'm going to hold shift. I'm going to plug that into T. So now what we've done is we've plugged all of this data, all these points are being moved twice, both in the positive and the negative x direction. And now I just need to give this a custom amplitude, basically, just a custom value. So all I'm going to do is go to math, divide this value by 12 like we did, like we've been doing because we're in feet, and give this a custom number. And this is going to be my dimension in inches that I want to use to offset our tertiary beam. So here, what I did there is I typed in 14, that's 14 inches, and I plugged that, the result of that division, into the F input of my vector, moving both of those points 14 inches away from the center of the primary beam. Hopefully you could see that there. And just to demonstrate this, if I change that value, you could see them moving back, moving out, so on. Good. Okay. Now the next step is a little bit of cleanup. If we look at the front over here, the front of the structure, I have a point dangling out in space here that I don't need. This one I want because I want a section there, because that's going to be important to draw my cladding. This one I don't need because the structure ends. That's also true for the other side over here. Don't need that one. So what I want to do is I also want to treat all of these points as a single list. That'll make my life a little easier when we start drawing the sections. So let's look at the output that we have here. We don't have that as a separate list right now. We've got a series of, basically, a series of lists. And each of these sets of points, the two of them, are on their own list. So the first thing I want to do is flatten this to make one list. And now if I look at the data coming out, it's one list of 46 points, as you can see. But I need to also resort them. I want to make sure that they're sorted so that the one that's closest to the origin over here in the x-axis is the first one in line, second, third, fourth, fifth, sixth, seventh, eighth, and so on. Right now that's not the case just because of the way that they were drawn. And this is a bit of a reverse engineering, which is kind of common in Grasshopper, where sometimes it's easier to draw a couple things out and then have to kind of manipulate the data later. So this is a good opportunity also to show you how to sort, which is a pretty common thing in Grasshopper. So the first thing we need to do is to sort these points is to figure out what we're sorting against. And we're going to sort them against their x coordinates. So let's go to vector, and let's deconstruct that point. So you're going to find that in the point panel, deconstruct. And now this has given us our x, y, and z value for each one of those points. We're only going to use the x as a way to organize this. And then we're going to go to set, list, and sort list. And the k input is numeric, the a input is geometric. You can kind of think about it that way. So basically, by sorting the numeric keys that are associated with the geometry that you got them from, you can resort that geometry based on those values. So basically, you can you can plug in x into k, and then you can re-input those points from the move component into the sort. And the output of this now is the same set of points, but reordered, so that like I said before, so that the one closest to the origin in its x value is the first one in the line, and then everything else after that is in order. And why that's useful is because what we're going to do is we're going to remove the first and last point in that list. All right, so we did this before when we got rid of a couple of curves, so we're going to do it again with points. So we're going to go to set, sequence, call index. The A output is the list that we're trying to change. And we need to give this both a 0, because that's the first one. So I'm going to grab a panel and drop in a 0. And then I'll get rid of my first one. Let me double check. Yep, that's gone. And now I want to get rid of the last one. And so the question is, what's the index of the last one? And now you can do that manually just by knowing how many things you have, or you can do it parametrically, which is obviously better. So you can click set up at the top, find the list length right here. And that'll tell you how long your list is. And in this case, we need to subtract this value by 1, because the index of that 46th point is actually number 45 because the first one is 0. So let's right click on that L output, go to expression, type in x minus 1. So now we've changed that value to 45. Hold the shift key, insert that into I, and reselect the call component so that we can see if it worked, and it looks like it did. It removed that one and it removed the first one. So that now, those two things have been basically removed from our data set because we don't need them. Okay, if that part made sense, good. If it didn't, maybe go back, try to do that one more time. If you have any errors, obviously raise your hand and we'll come through. This is important because now the next thing we can do is put a plane on each of these points and use that plane to cut our sections through the surface. So the plane that we need is in the YZ direction because the curves that we want to draw are in that axis. So let's go to vector, plane, YZ, draw YZ plane at all those points. We don't have to visualize those, we can just turn off that preview. And then the next thing is to go to intersect, mathematical, and you'll find your BREP plane component, which is otherwise known as a section as it's being described here. This is how you take sections through objects. There's no section command or no section component in Grasshopper. It's called this. The BREP is the surface, and the planes are the ones we just drew. And let's turn off that offset surface for a minute and have a look at the result of what we just did here. And you can see now that we've drawn our curves floating above this is the start, the rail curve for the tertiary beams. They float above the secondary and they're offset to our specified distance, which is 14 inches from the center of the primary beam. It's pretty nice. Now the sectioning could sometimes take time. So when you're doing when you're later on down the line when you're making changes to this file, and you make let's say a change here or a change somewhere else downstream, you're going to have to give the computer just a second to update itself, just as a warning. Okay, so now that we have our rails, we could start sweeping. And we need a perpendicular frame once again at the end here. So that's simple. We can just go to curve, analysis, perpendicular frame. Here's our curves. We're also going to probably need to reparameterize this. So go ahead and right click on that C input, reparameterize that, and grab a slider. And let's see where this puts our frame here. Yeah, it's going to put it on the other side. So just because I'm already on this side, I'm just going to put this over to 1. Either one of these will work, either 0 or 1. It's up to you. I'm going to leave it at 1, so I can see it. And again, we don't need to see that frame, so let's drop that out. And let's draw a rectangle or a square right there. So we'll go back to curve, primitive, rectangle. The frames are the P. Input is coming out of is of course the frame. And now we need to give this an X and a Y value, but let's say we want these to be the same size as our secondary. We can just borrow the same domain that we used to draw those secondary beams like that. And because I organized my script relatively well here, I didn't have to go searching for this. This was right where I left it last time, and I was able to just simply plug it right in. And now when we look back, we can really see that kind of list of dependencies growing nicely. It's branching off from this numeric domain to our tertiaries and then up to our secondaries. So if we have to make any changes, we kind of know where to find it, as opposed to having overlapping lines everywhere. It could be pretty confusing. So you want to pay a little bit of attention to that as you work. All right, let's do our sweeps. Sweep, freeform, surface, freeform, sweep 1. Section curves there. And the sections are the curves, like this. Good. We could cap these like we did before, so we could type in cap those, turn off that preview, and let's give this thing a custom color. So let's take our preview from up here, copy and paste it. Let's drop that in, turn those off, and then change the color. I'm going to make mine kind of magenta. Has a decent color palette. Now we've got our tertiary members drawn. Let's check for collisions. It doesn't appear that we have any. Looks like we're actually pretty good here. If there are collisions, you can go back to the parameter that set that gap, which was here. And that should lift them, but it's going to take a little bit of time. And there you go. It's very subtle, but it does move if you pay attention. And I think the offset on that looks quite good. No collisions. And we're set. So while we're here, let's just keep going. The next step to wrap this thing up is to just draw the cladding. And to draw the cladding, all I need to do is take the center curves, the sections, offset those above our purple beams to a value that we can customize, and then start lofting in between. So let's start with that. What we're going to do is just go to Math, and we're just going to simply add a value, because this is, remember, this is the size that we used to draw basically the dimensions, the half dimension of the cross section of the tertiary and secondary. And I'm going to drop this somewhere else down here so it's a little easier to find. And then this value is going to be our actual offset, so I'm just going to type in like 2 for now. Okay. So that's our offset. Go to Curve, grab in Utilities, grab the Offset Curve component. The curves that we're offsetting are the sections. Remember these? Those are the ones that we just swept. The distance is the value that we're just plugging in here. That looks a little bit large. We'll fix that in just a second. The plane, remember, we need a YZ, so let's go to Vector, Plane, YZ. That should fix the ups and downs. Looks like we don't have to reverse this, but we do need to divide it by 12. Math, divide. And that'll make it in inches before we're in feet. Okay. Okay. If your Rhino units were in feet, you would not have to go through that division process. But sometimes there's an advantage to that, sometimes there isn't. In this case, because we drew our Rhino curves in feet, I'm just going along with it. But you can obviously change the Rhino units to be in inches, and you would not have to divide these. So it's important that when you open this script that you're always in feet. Otherwise, all of this will be divided. All of your inches will be divided, and that would be a problem. So when we save this file, you want to make sure to reference that. Anyway, the offsets are now drawn. You can kind of see them floating above the purple beams. And the next step is to get these organized so that I can sweep from this one to that one, have a gap, that one to that one, have a gap, that one to that one, have a gap. Okay. And now, no matter this is a good thing. No matter it doesn't matter how many of the primary beams we have, if that's an odd or an even number, because if we multiply that number by 2, it will always be an even number. And the reason why we need to know that is because what we need to do now is take these curves, which have no organization, they're just kind of drawn for us in an order. We're going to flatten those, and then we're going to repartition them into sets of 2. So we're going to go to Set, List, Partition, plug your C output into the L input of partition, and then grab a panel and just type in 2, then let's have a look at what the result is. If we hover over, we now have list chunks. So it took all of those lines in order and turned them into sets of 2, which we can use to our advantage when we do our lofting. So let's go to Surface, Freeform Loft, and plug that in. And that's going to give us the separate, basically surface panels that go across the entire structure, leaving our gaps. And if we didn't do this partitioning, you would have a continuous surface, like this. But because we did our partitions, it's going to make a set of separate lofts. Okay? Nice little, decent little trick. And that is basically that. Let's double check to see if we have any collisions. Doesn't look like we do. Looks like my offset's fine. If I wanted to change that, I could here. That's getting a little tight, so let's bring that back up to 2. And we are more or less done. The last thing I want to do is just add a custom color to this. So I'm going to grab that custom preview with the swatch from up top and change the color. Okay. So that's that. That's your surface. And then now that we've completed our script, we should test it. Okay. And in the last few minutes of this tutorial, what I'm going to do is I'm just going to kind of walk through the parameters that we have and see if everything works out. So let's change the number of primary beams to something else. Let's just say 18, and let's let it think. That updates without any issues. So we've changed the number. Let's go back. Very good. We can change the size of these primary beams. I don't have any problem with that, I'm sure. That's related to the gap in between. Let's go over here. The number of secondary beams, let's play with that a little bit. And that updated really quickly, so the blues are quite quick of an update. We can add a lot of these if we like. No trouble, very fast. Well, let's make it 16. I think that looks pretty good. Make it more of a dense structure. And now our sections, let's find those. Those are here. That's related to how many primary beams we have, but we can at least affect how far apart they are. So let's do that. Let's try this out. Let's say something like 8 inches to make that gap much smaller. There we go. Looks like there might be a little bit of an issue in there in terms of our loft. Let's see if we can, yeah. Okay, that's something to watch out for. I'll do a little testing to see what's breaking there. But it looks like if we get too close, we might end up with an error. But that offset, I think, wouldn't probably be any smaller than this anyway, because we're getting to the point now where we're actually occluding the primary beam. So in this kind of structure, there's a minimum anyhow. And if we plug in, a different value into there, we got to let the computer think a little bit so that it makes the, okay, great. So this looks pretty good. I think it's a pretty great start at making a fully parametric model of the Crystal Bridges structure without all the details. The main, primary, secondary, and tertiary, and skin are all included and can be updated. Okay, that's it. Thank you.